Contemporary Amperex Technology, or CATL, recently unveiled their first generation sodium-ion batteries for commercial use. I've been hearing a lot about this technology and thought it would be worth talking about. Scientists started off developing sodium-ion batteries right alongside lithium-ion batteries. Over time, lithium rose to dominance and sodium fell by the wayside. But now things have changed, and sodium-ion batteries have started to see renewed interest. In this video, we will briefly review sodium-ion batteries, their state of development, and what their commercialization means for the renewable energy market at large. But first, please consider subscribing to the Asianometry newsletter. If you subscribe to the channel, you should also subscribe to the Asianometry newsletter. Check out the newsletters for the full scripts as well as additional commentary after the fact. You can find the link to the newsletter in the video description below, or you can just go to asianometry.com. As of right now, you can expect a new newsletter every Thursday at 1 a.m. Taiwan time. Much thanks. Sodium-ion batteries share a similar structure with lithium-ion batteries. They have a cathode, an anode, a porous separator between the two, and an electrolyte. When the battery is being used, ions migrate back and forth between the cathode and the anode. The primary difference between the two battery types is that their components are made of different compounds. That is actually part of the appeal. It is likely that commercial sodium-ion batteries can share the same engineering and production methods as lithium-ion batteries. The single biggest advantage that sodium-ion batteries have over lithium-ion batteries has to do with the availability of certain raw materials, and linked to that, cost. Almost all of the world's lithium comes from 4 countries: Australia, Chile, China, and Argentina, and this element is not particularly easy nor environmentally friendly to extract. Furthermore, there are other critical elements like cobalt which present particularly large environmental and humanitarian concerns. The global supply of sodium, by contrast, is essentially unlimited. There are over 1,000 times more sodium than lithium in the Earth's crust. This translates to a raw ingredient cost of $150 per ton as compared to lithium's $5,000, a 30 times decrease. Researchers have been trying to commercialize sodium-ion batteries side by side with lithium-ion batteries. Development kicked off in the early 20th century when it was discovered that molten salts were capable of conducting high amounts of sodium ions. In 1968, scientists at the Ford Company developed a sodium-sulfur battery for use in electric vehicles. It was essentially made of a tube of metallic sodium dipped into another tube of liquid sulfur. Ford felt that a 350-pound sodium-sulfur battery could provide 200 to 300 miles of range for a 1,350-pound car running at 40 miles an hour. The minimum charge time was said to be half an hour. The biggest challenge was that it only worked at very high temperatures, 570 to 660 degrees Fahrenheit, or 300 to 350 degrees Celsius. As you might expect, this caused safety and longevity issues, especially in cars. For instance, at those temperatures, the aluminum-based container tubes would react with the battery chemicals and rupture. Ford never was able to commercialize the technology for a working electric vehicle, and it makes a lot of sense why molten salt batteries, as they are called, have yet to see wide use in mobile electronics. But they do have several real-world applications. The most common is to provide power for guidance systems and missiles. But they are also ideal for extreme environments. I just finished a video about using them on the surface of Venus. Ford eventually sold this technology to a Japanese company called NGK. Today, they are sold as stationary battery solutions for peak energy use and grid stabilization. The oil crises of the 1970s revitalized interest in this technology. In 1985, South African researchers created a new version of the molten salt battery using nickel chloride and sodium tetrachloroaluminate. The Zebra battery, as it was called, held a lot of promise. But in 1989, Sony successfully commercialized the lithium-ion battery, and its advantages quickly won over the industry. From then on, research largely focused there. Today, lithium-ion battery technologies largely dominate the industry. They are the first choice for use in electric vehicles, stationary batteries, and mobile gadgets. But in the 2000s, concerns began emerging with regards to the supply of raw materials. Like as I mentioned earlier, natural sources of lithium are limited, and that cannot be the case if we want to be truly serious about a carbon-free economy. Secondly, a less heralded reason has to do with intellectual property rights. So many patents have been filed around lithium-ion technologies that new companies have to be extremely careful not to run afoul of the lawyers. Sodium-ion battery technologies, by contrast, offer far larger green fields. Thus, starting in the 2010s, people started taking a second look at sodium-ion batteries, which would again use sodium, but at room temperatures. The number of publications relating to sodium-ion batteries began to quickly rise, and in recent years have even surpassed that of lithium-ion batteries. Batteries, especially prototypes, wildly differ from one another, but for the most part, scientists have started to hone in on a few high-potential sodium-ion battery chemistries. Most studies have converged on making the anodes from a substance called, quote, hard carbon, end quote. It can also be colloquially described as charcoal. The electrolyte makes sure that sodium ions can travel from the anode to the cathode. These have to be of low viscosity, high conductivity, and be electrochemically stable. Researchers have generally chosen sodium salts dissolved in solvents of organic carbonate, though there is plenty of research advocating for other options too. I won't cover them here. The cathode is where much of the latest research has been focused on, same as with a lithium-ion battery. Makes sense since the cathode is the single most expensive component in the whole thing and is key to its overall viability. Many candidate materials have emerged as potential contenders. The most common and most closely studied class of cathode material are sodium-layered oxides. These are pretty wild. They have a crystalline structure made up of sheets of metal oxides with sodium ion sandwich in between. They are distinguished with a P2, O3, and P3 notation that refers to their geometries. And the reason why they show so much promise is because their crystalline structures have a lot in common with that of lithium cobalt oxide, the first legit cathode material in lithium-ion batteries. There has been a whole lot of research in cathode materials for sodium-ion batteries. Other research candidates include sulfides, phosphates, fluorophosphates, carbonophosphates, vanadium-based polyanionic compounds, and so on. CATL, for their part, has opted to make their cathodes out of something else. There has been a whole lot of experimentation in past years. The science has moved fast, and the first few sodium-ion battery products have started to inch towards the market. The first actually commercial-ready sodium-ion battery looks to be an 18650 cell created by the French research agency CNRS-CEA in 2015. 18650 is a standard format size and refers to the battery's dimensions, 18 mm wide, 65 mm tall, and the 0 means that it is a cylindrical format. The reported energy density is about 90 watt-hours per kilogram. 2 years later, in 2017, the agency spun off the research into a startup called Tiamat Energy. The company's long-term objective is to develop low-voltage systems for hybrid vehicles and help ensure French technological sovereignty. In June 2020, researchers at Washington State University and Pacific Northwest National Laboratory announced a more advanced sodium-ion battery. Its creators speculate that the battery might be able to achieve a practical specific energy of about 160 watt-hours per kilogram. This is comparable to current lithium iron phosphate batteries. That being said, we should temper our expectations here. Sodium has lower ionization potential or ionization energy than lithium. This means that sodium-ion batteries will have lower energy densities and operating voltages than their lithium counterparts, and it is not clear whether they can ever catch up to top-line lithium-ion batteries in this regard. There are also a number of other technology startups trying to commercialize sodium-ion batteries. Some examples include UK-based Faradion Limited, Sweden-based Altris AB, China-based Haina Battery, and US-based Natron Energy. Now that we have very briefly gone over the current state of the research in sodium-ion batteries, we can review the CATL announcement and get some perspective here. In their announcement, CATL gave a few details about how their sodium-ion battery works. The anode is made of hard carbon, as is commonly the case. They noted that their hard carbon anode features a unique porous structure which lengthens its cycle lifetime and allows for more sodium-ion movement. For the cathode, however, they are using something interesting. they mentioned that they're using a substance called Prussian white. Prussian white is an analog of a pigment called Prussian blue. First synthesized over 300 years ago, the dye makes a beautiful blue shade and has been noted for removing heavy, toxic metals from the body. It is very cheap, easily made, and non-toxic. But sometime in the early 2010s, researchers also noticed its suitability for use in sodium-ion battery cathodes. They have good discharge rates and can sustain their capacity over many charge cycles. Some tests have shown 95% retention even after 10,000 cycles. One big drawback of Prussian blue cathodes, and there will always be drawbacks, is that they lose a lot of their capacity in the presence of moisture. Other companies have been exploring Prussian blue cathodes. Notable companies include the aforementioned Altris AB and Natron Energy. CATL said that their first-generation sodium-ion battery can achieve energy densities of up to 160 watt-hours per kilogram. This is comparable to the Washington State battery unveiled last June, which, as I mentioned, is in turn competitive with current lithium-ion phosphate batteries. The second generation hopes to be over 200 watt-hours per kilogram. Furthermore, like as I also mentioned, the engineering and manufacturing processes are similar between sodium and lithium-ion batteries. So CATL can really take advantage of this by tightly integrating their sodium-ion offering into their existing lithium-ion infrastructure and product ecosystem. It is worth keeping in mind, though, that since the two preparatory processes will have so much overlap, sodium-ion battery costs will not be drastically lower than lithium-ion batteries. Most of the savings will come from cheaper raw material costs. It is like how gasoline prices don't rise and fall in step with oil prices. One paper estimates that the end users will see 10 to 30% price savings using sodium-ion, with all things being equal. The company also called out battery system integration capabilities where they can mix and match sodium and lithium-ion batteries into a single system. Lithium-ion batteries, which right now have higher energy densities, are automatically used by the system when sodium-ion falls short. So that is kind of interesting. We talk a lot about new and exciting battery chemistries, but the reality is that a lot of these concepts do not see commercialization and far fewer get widely adopted. For instance, lead-acid batteries have been around for 150 years. Their energy densities are not comparable with lithium-ion, and their materials are quite toxic. Yet because lead-acid batteries are cheap and reliable, they are still very widely used. In 2020, global lead-acid battery sales totaled nearly $50 billion. So inertia really means a whole lot. So not everything will be a lithium-ion battery level of success, and it looks like sodium-ion batteries will never be able to replace lithium in certain use cases like mobile phones and other electronic gadgets. But they have potential in short-range electric vehicles and especially in stationary power systems, places where space is less of a big deal, making their lower energy density not so much of a confounding factor. For instance, energy storage for solar and wind renewables. Those areas which operate at scale can also really appreciate the cost savings. There are already some small startups in the space, but CATL is no ordinary enterprise. They are the biggest battery company in the world, and it appears that they will pour a lot of resources into this endeavor, leveraging their size, manufacturing skill, and R&D savvy to make this work. Let us see if they will succeed and help sodium-ion live up to its full potential. Alright everyone, that's it for tonight. Thanks for watching. Remember to hit up the email newsletter, like I said, and sign up. Check out the Patreon if you want to support the work and watch any of the early access videos. Like, subscribe, all that good stuff, blah blah blah. And if you want to send me an email, then drop me a line at john@asianometry.com. I love reading your emails and I try to get back to you as soon as I can. Until next time, I'll see you guys later.